They returned after a 158-day trip to Antarctica that began in November. They completed 45 scientific research projects in the polar region, including the discovery of a superkaon.
Chinese researchers just scanned Antarctica, and what they found under the ice is being covered up. 5 kilometers of frozen silence. And beneath it, something that has shaken governments to their core. Structures that should not exist. Life that defies every scientific model we have. This is not a theory. This is not speculation. The data is real, and the world's most powerful nations are scrambling because of it.
Major powers are turning their eyes north, looking for resources, new routes through the ice, and a way to strengthen their position on the global stage.
A lot of countries have come out with Arctic strategies. It's part of how the international order is being challenged.
They have been there for years. They knew something was down there, and they never told you. What is buried under Antarctica is about to change everything. Watch this before it disappears. There is a place on this planet where the temperature can fall to minus 89 degrees Celsius, where winds exceed 300 kilometers per hour, where the sun disappears entirely for months at a time, and the darkness is so complete that it becomes difficult to separate the sky from the ground. Most people will never go there. Most people will never need to. And yet, what happens in that place the next few decades may affect every single person alive today. This is Antarctica, and right now, quietly, several of the world's most powerful nations are racing to establish control over it. To understand why, you need to look past the surface, past the ice, past the storms, past the sheer hostility of the environment. Because buried beneath roughly 5 kilometers of frozen water lies something that has drawn the attention of governments, scientists, military strategists, and economists alike. Resources, data, power, and a deadline that is closer than most people realize. Let us start with what is already known, because the scale of this continent alone is enough to shift your perspective entirely. Antarctica is larger than the United States and Mexico combined. It holds approximately 70% of all the fresh water on Earth, locked inside an ice sheet so thick that entire mountain ranges sit buried beneath it, invisible from above. The continent is not simply large in the way that Russia or Canada is large. It is large in a way that makes it feel almost abstract. You can fly for hours in a straight line and still be nowhere near the edge of it. There are regions that have never been visited by a human being, not because they are particularly dangerous to reach, but simply because no one has had a reason to go there yet. That is changing. China has, over the past decade, significantly expanded its presence on the continent. It has constructed year-round research stations equipped with technology designed to function in some of the most extreme conditions on Earth. Its newest facility, built on the interior plateau, where temperatures regularly drop to minus 60 degrees Celsius, represents a serious long-term investment. The station is supported by autonomous vehicles, drone systems, and satellite networks that provide real-time data coverage across enormous distances. This is not the infrastructure of a country conducting casual scientific research. This is the infrastructure of a country that intends to be there for a very long time. Russia has maintained a continuous presence at Vostok Station, one of the most remote research outposts on the continent, for decades. Russian teams have carried out extensive seismic surveys across Antarctic waters, mapping what lies beneath the seabed with equipment capable of identifying potential oil and gas deposits. The commitment involved in sustaining operations at that level, in that environment, over that length of time, is a signal in itself. The United States, meanwhile, is facing a different set of problems. McMurdo Station, the largest research hub on the continent and the backbone of the American Antarctic program, is more than 60 years old. It requires constant maintenance. Funding pressures have made upgrades difficult, and the gap between American infrastructure and that of its rivals has been growing steadily. The balance of presence on the continent is shifting, and it is shifting in a direction that has not gone unnoticed in Washington. All of this activity is technically restricted by a legal agreement that has been in place since 1959. The Antarctic Treaty, signed originally by 12 nations and now supported by over 50, designates the entire continent as a zone for peace and science. It prohibits military activity, suspends all territorial claims, and bans any form of resource extraction. In 1991, the Madrid Protocol strengthened those protections by adding a 50-year ban on mining. That ban can be reviewed in 2048. It is worth being precise about what that means. A review in 2048 does not automatically lead to mining. It does not mean that the treaty collapses or that countries will immediately begin extracting resources. What it means is that the conversation can officially begin. And in international negotiations, the countries that have the most established presence, the most comprehensive data, and the strongest logistical infrastructure tend to have the most influence over how those conversations go. Presence in this context translates directly into leverage. So what is actually down there that justifies this level of investment and strategic maneuvering? Part of the answer is scientific, and it is genuinely extraordinary. Antarctica is, in the most literal sense possible, a record of Earth's entire atmospheric history. Every year, snow falls across the continent. Over time, that snow is compressed under the weight of the layers above it. As it compresses into ice, tiny pockets of air become trapped between the crystals. Those pockets are not symbolic. They are actual samples of the atmosphere from the year that snow fell. They are sealed inside the ice, perfectly preserved, sometimes for over 1 million years. Scientists extract this record by drilling deep into the ice sheet and pulling up long cylindrical samples known as ice cores. The deeper the core, the further back in time it reaches. One of the oldest ice cores ever recovered was drilled from nearly 3 kilometres below the surface. The air trapped inside it is approximately 1.2 million years old, dating to a period when early human ancestors were just beginning to shape basic stone tools. That air has been sitting undisturbed ever since, waiting. The data contained in those cores is not simply historically interesting, it is practically valuable in ways that directly affect how governments and industries plan for the future. By analysing the trapped air, researchers can measure carbon dioxide levels, methane concentrations, volcanic ash deposits, and temperature signals across vast stretches of geological time. This gives scientists a detailed picture of how Earth's climate has shifted across hundreds of thousands of years, including periods when the Sahara was a green and fertile landscape, when woolly mammoths roamed across frozen continents, and when atmospheric carbon dioxide sat at roughly half its current level. That kind of baseline data underpins. Climate modelling informs resource planning and shapes international environmental policy. Governments and research institutions invest heavily in it for exactly that reason. If that ice melts, the record it contains is gone, not archived somewhere, not transferred to another format, gone permanently. Which means that whoever controls access to Antarctica controls access to data that has no equivalent anywhere else on Earth. There is also something called blue ice, found in areas where powerful winds strip away fresh snow and expose the compressed layers beneath. Unlike regular ice, blue ice has had all of its air bubbles forced out by the extreme pressure of the layers above. When sunlight hits it, the ice absorbs the red and yellow wavelengths and reflects blue, producing a striking electric colour that can stretch across entire fields. Some of these blue ice surfaces are hundreds of thousands of years old, exposed directly on the continent's surface. Standing on them means standing on something that formed before modern humans existed. None of this is incidental to the geopolitical race. It is central to it. The scientific value of Antarctica gives every nation a legitimate reason to be there. Research stations justify permanent infrastructure. Permanent infrastructure justifies investment. Investment builds presence. And presence, as 2048 approaches, is exactly what each of these nations is trying to accumulate. The science and the strategy are not separate tracks. They run together, and they always have. What lies beneath the ice itself, the hidden geography, the buried resources, the living systems operating in total darkness, is where the stakes become even harder to ignore. But to understand that, you first need to grasp just how little of this continent has actually been seen. Most people, when they picture Antarctica, imagine a single frozen mass sitting at the bottom of the globe. A uniform sheet of white, static, and unchanging. The reality is considerably more complicated and considerably more strange. Beneath the surface of this continent, systems are moving, water is flowing, and life is surviving in conditions that, until relatively recently, scientists believed could not support it at all. Start with the ice itself, because even that is not behaving as a single unified system. Antarctica is effectively split into two very different regions, and they are responding to the current climate in opposite ways. In West Antarctica, glaciers are accelerating toward the ocean. Ice shelves, which are the floating extensions of the ice sheet that reach out over the sea, are breaking apart. Some of the fastest rates of ice loss currently being recorded anywhere on Earth are happening in West Antarctica, and the pace has been increasing. Satellite measurements have confirmed this consistently over the past several decades. East Antarctica tells a different story. It is colder, the ice is thicker, and in some areas snowfall is actually adding to the ice sheet rather than depleting it. The region is more stable, though researchers are careful not to describe it as immune to change. The overall picture, when you account for both regions together, is one of net ice loss. But the fact that two parts of the same continent are doing almost opposite things at the same time makes predicting future behavior extremely difficult. It also makes the location of research stations strategically important because the data any given station collects is entirely dependent on where it sits. Choosing the right location means having access to the right information, and that information has both scientific and commercial value. Below the ice, the situation becomes stranger still. Between the base of the ice sheet and the bedrock underneath, water is moving. Not in small quantities and not slowly. Antarctica contains thousands of rivers and lakes that exist entirely beneath the ice, forming a connected drainage system that researchers are only beginning to map properly. Some of these subglacial lakes hold volumes of water comparable to major surface reservoirs. When they drain, the process can be surprisingly rapid. Billions of litres can be released over just a few days, travelling through underground channels that have never been directly observed. When large volumes of water shift beneath the ice above responds. The surface can rise or fall by several meters as pressure redistributes underneath it, in the same way that a thin shell deforms when weight moves across it. Scientists monitoring the surface of the ice sheet with satellites have recorded these movements and used them to trace the drainage events happening below. It is one of the few ways researchers can study a system they cannot physically access, and physical access is extremely limited. If you were to add up every location beneath the Antarctic ice sheet that humans have actually reached and sampled directly, the total area would be roughly the size of a basketball court. On a continent larger than the United States and Mexico combined, that is essentially nothing. The vast majority of what lies below has never been touched and in many cases, never been directly observed. To work around this, scientists use aircraft equipped with electromagnetic sensors and ground-penetrating radar systems. These instruments send signals down through the ice and rock, and the way those signals return reveals whether the material below is frozen, liquid, or moving. The technique is broadly similar in principle to the way bats use sound to navigate in darkness. It allows researchers to build detailed maps of subglacial features without ever drilling into them. China has invested heavily in this kind of technology and currently operates some of the most advanced ground-penetrating radar systems being used on the continent. The mapping work being done with these tools is helping to identify subglacial water channels and potential resource deposits at a pace that other nations have struggled to match. Occasionally, the hidden systems beneath the ice break through to the surface in ways that are impossible to ignore. One of the most striking examples sits at the edge of Taylor Glacier in the McMurdo Dry Valleys region. A stream of deep red water flows out from the glacier's face, staining the surrounding white ice as it goes. It is called Blood Falls, and when it was first observed by explorers in 1911, no one could explain it. The explanation, once scientists eventually worked it out, turned out to be remarkable. The water originates from a brine reservoir sealed beneath approximately 400 meters of ice. It is ancient water, estimated to have been isolated from the surface for somewhere in the region of several million years. It is more than twice as salty as normal ocean water, which keeps it liquid even at temperatures of around -5 degrees Celsius. The water itself actually emerges clear. The red color appears immediately, on contact with the open air. The brine is rich in dissolved iron, and when that iron is exposed to oxygen, it oxidizes rapidly, producing the vivid red staining. It is essentially the same process that causes metal to rust, happening on a continuous basis across a glacier face. What Blood Falls demonstrates is what these hidden rivers are actually carrying: iron, organic carbon, and nutrients that have been accumulating in isolation for millions of years. There are thousands of outflow points like this distributed across Antarctica, most of which never reach the surface. But when nutrient-rich subglacial water does enter the surrounding ocean, it triggers a chain of events with consequences that extend far beyond the continent itself. The nutrients feed microscopic organisms called phytoplankton, which form the base of the Southern Ocean's food web. Phytoplankton feed krill, small crustaceans that exist in extraordinary numbers in Antarctic waters and represent one of the largest animal biomasses on the planet. Krill feed fish, seabirds, seals, and whales, including blue whales, the largest animals known to have ever existed on Earth. The entire structure of the Southern Ocean ecosystem, from the microscopic to the enormous, is connected to what flows out from beneath the ice. Krill also has direct commercial value. Krill oil is used widely in dietary supplements and pharmaceutical products, and global demand has been growing. Nations with a strong research presence in Antarctica are better positioned to monitor krill populations, understand the conditions that sustain them, and influence the international agreements that govern how they are fished. The connection between subglacial hydrology and commercial fishing is not obvious at first glance, but it is real, and it is one of the reasons why understanding what moves beneath the ice has practical economic implications. Beneath all of this, at depths exceeding 3.5 kilometers below the surface, lies Lake Vostok. It is one of the largest lakes on the planet by volume, stretching roughly 240 kilometers in length and 50 kilometers in width. It has been completely sealed beneath the ice for an estimated 15 million years. No sunlight has ever reached it. It has had no contact with Earth's atmosphere longer than modern humans have existed as a species. When Russian scientists finally drilled down and reached the lake's water in 2012, after decades of drilling work, the samples they brought up contained evidence of microbial life. Organisms survive without sunlight, without warmth in any conventional sense, and without any of the conditions that most life on Earth depends on. Lake Vostok is not unique in this regard. There are close to 700 subglacial lakes distributed across Antarctica, and in the small number that have been sampled, evidence of life has been found consistently. Microbes extract chemical energy directly from rock. Microbial DNA preserved in sediment layers. Life operates on entirely different rules. This has implications that go well beyond Antarctica. The conditions inside these sealed lakes, cold, dark, and isolated beneath thick ice, are comparable to the conditions thought to exist inside certain moons in the outer solar system. Europa, one of Jupiter's moons, is believed to have a liquid ocean sealed beneath a frozen shell. Enceladus, orbiting Saturn, has been observed venting water vapor from beneath its ice. If microbial life can survive for millions of years in the dark beneath Antarctic ice, then the possibility of life existing in similar environments elsewhere in the solar system becomes significantly more credible. Antarctic subglacial research is, in a direct and practical sense, informing how scientists think about the search for life beyond Earth. The organisms found in these environments also have potential applications in biotechnology. Microbes that function at near freezing temperatures and derive energy from chemical reactions, rather than sunlight, represent a biochemical toolkit that has barely been explored. Researchers have suggested possible applications in areas ranging from food preservation to pharmaceutical development to technologies relevant to deep space exploration. The commercial interest in Antarctic microbiology is still at an early stage, but it is growing. And beneath even the subglacial lakes, there is heat. West Antarctica sits above a chain of volcanoes, most of them hidden entirely beneath the ice. Some of these volcanoes show signs of current activity. The weight of the ice above suppresses the kind of explosive eruptions associated with surface volcanoes, but heat still builds beneath the rock. That heat melts ice from below, creating chambers of water and steam beneath the glacier. It destabilizes the ice sheet from underneath and contributes to the accelerated movement of glaciers in ways that early climate models did not fully account for. Ice cores have preserved layers of volcanic ash from eruptions that occurred while the ice was forming above them, providing a record of activity stretching back hundreds of thousands of years. The presence of active volcanic heat also raises a more immediate practical point. In a continent where there are no conventional fuel sources and where supplying energy to research stations requires enormous logistical effort, geothermal energy represents a potential alternative. Tapping into volcanic heat to power year-round facilities would reduce dependence on fuel shipments and make permanent operations significantly more sustainable. That kind of energy independence in one of the most logistically challenging environments on Earth would represent a meaningful strategic advantage for any nation able to develop it. What exists beneath the Antarctic ice is not a simple void. It is a connected, active, and in many places living system, operating on timescales and under conditions that have no real parallel anywhere else on the planet's surface. And it sits directly beneath a continent whose geology holds some of the most significant mineral deposits on Earth. Strip away the ice from Antarctica entirely, and what you find underneath is not a flat, featureless plain. It is a landscape of extraordinary complexity, shaped over hundreds of millions of years by the same geological forces that built the continents we live on today. There are mountain ranges down there that rival the Alps in scale, sitting in complete darkness beneath kilometers of ice, unseen for millions of years. There are canyons deeper than anything on the surface of the Earth. There are ancient river valleys, preserved almost exactly as they were tens of millions of years ago, running between ridges and basins that have never been touched by sunlight in longer than the human species has existed. The Gamburtsev Mountains stretch across the interior of East Antarctica, with peaks rising several thousand meters above the surrounding bedrock. They were discovered in 1958 by a Soviet geophysical expedition using seismic equipment to measure what lay beneath the ice. Decades later, an international research project used airborne radar and gravitational measurements to map them in detail. The results were striking. The mountains are comparable in size and topographic relief to the European Alps, yet they sit entirely beneath the East Antarctic ice sheet, invisible from above and inaccessible from below. How they formed and why they remain so well preserved after so long is still not fully understood. Further west, Denman Canyon cuts through the bedrock at a depth of more than 3.5 kilometers below sea level. It is the deepest land canyon on Earth, deeper than any canyon found on any other continent, hidden beneath the ice. The glacier that flows through it, Denman Glacier, is one of the fastest moving in Antarctica and has been losing ice at an accelerating rate. Because the canyon floor sits so far below sea level, warm, ocean water can potentially intrude from the coast, getting underneath the glacier and melting it from below. Researchers have identified this as one of the more significant vulnerabilities in the Antarctic ice sheet, with implications for long-term sea level projections that affect coastlines across the entire planet. East and West Antarctica are not simply different in terms of how their ice is behaving, they are fundamentally different geological structures. East Antarctica is ancient and stable, built on some of the oldest rock on Earth. West Antarctica formed through a different process entirely. Over millions of years, tectonic forces stretched the crust apart and thinned it, creating a series of deep basins well before any ice arrived. That thinning brought the Earth's internal heat closer to the surface, which explains the presence of active volcanoes beneath the western ice sheet. When the climate cooled enough for ice to begin accumulating on the continent, those low-lying basins filled first. Remove the ice today, and much of West Antarctica would sit below sea level, submerged beneath the ocean. What the rock itself records is perhaps the most striking part of all. Fossilized pollen, preserved root systems, and plant material found in Antarctic sediments show that this continent was once a very different place. Tens of millions of years ago, before the ice arrived, Antarctica had rivers, forests, and a temperate climate capable of supporting a complex ecosystem. The bedrock still carries the physical imprint of that era in the form of ancient drainage channels and soil structures that formed when liquid water ran freely across the surface. It is geological evidence of a world that no longer exists, preserved in a place that has since become the coldest and most inhospitable environment on Earth. This buried geology is also what connects Antarctica to some of the most resource-rich regions on the planet. Antarctica was once part of a supercontinent called Gondwana, which also included what is now South America, Africa, India, and Australia. Those landmasses share deep geological ancestry with Antarctica, and they are among the most mineral-rich regions on Earth. South America has some of the world's largest copper and lithium deposits. Africa holds enormous reserves of platinum, cobalt, and rare earth elements. Australia is a major producer of iron ore, nickel, and gold. The geological surveys carried out in Antarctica suggest that the same types of formations that produce those deposits exist beneath the Antarctic ice sheet. Estimates of the potential value of those resources run into the trillions of dollars. Coal, oil, natural gas, copper, nickel, platinum, and rare earth elements, all of which are critical to the production of electronics, batteries, and the renewable energy infrastructure that countries around the world are currently racing to build. For now, every one of those resources is legally off-limits. The Antarctic Treaty, which came into force in 1961, prohibits any form of resource extraction and suspends all territorial claims. The Madrid Protocol, agreed in 1991, added an explicit 50-year ban on mining activity. But that ban is not permanent in the same way that the original treaty is. In 2048, the protocol can be reviewed, and if 3/4 of the consultative parties to the treaty agree, the rules governing resource extraction could be changed. It is important to be clear about what this means and what it does not mean. A review process beginning in 2048 does not guarantee that mining will start. The treaty has broad international support, and there is significant scientific and public opinion in favor of maintaining Antarctica's protected status. Environmental organizations, research institutions, and a number of governments have stated clearly that they want those protections to remain in place. But the review process creates an opening for the rules to change, and in international negotiations, the outcome is rarely determined solely by principle. It is determined by who has influence, and influence in this context comes from presence, data, and infrastructure. This is precisely why the strategic positioning happening on the continent right now matters as much as it does. The countries that have built the most comprehensive research networks, mapped the most territory, and established the most durable year-round operations will arrive at that 2048 review with a stronger hand than those that have not. Every station built, every survey conducted, and every dataset collected between now and then is also a form of preparation for a negotiation that could determine the future of the most resource-rich, untouched territory on Earth. China's approach to this has been methodical and well-funded. Over the past 2 decades, it has gone from being a relatively minor player in Antarctic research to one of the most active and technologically capable nations operating on the continent. It now runs multiple research stations, including year-round facilities in some of the most demanding locations. Its most recent station, built on the interior plateau, is designed to operate continuously in temperatures that routinely fall to -60 degrees Celsius. The logistics required to build and sustain a facility in that environment are considerable, and China has invested heavily in the supply chain to support it, including purpose-built polar research vessels and a growing fleet of aircraft capable of operating in extreme cold. The investment in ground-penetrating radar and autonomous survey technology has allowed Chinese researchers to map subglacial features, water channels, and potential resource deposits across large areas of the continent faster and more comprehensively than most other nations have managed. Russia's engagement with Antarctica is older and in some respects even more deeply embedded. Vostok Station, operated by Russia and situated near the geomagnetic South Pole, is one of the most isolated research outposts on Earth. Sustaining a continuous human presence there for decades through the most extreme winters the continent produces represents a logistical and operational commitment that most countries would find difficult to match. Russian teams have conducted extensive seismic surveys of Antarctic waters, generating detailed maps of the seabed geology in areas that are of significant interest from an oil and gas perspective. That body of survey work represents years of accumulated data that would be directly relevant to any future resource extraction discussions. The United States has historically been one of the dominant forces in Antarctic research. McMurdo Station, the largest facility on the continent, serves as the logistical hub for American operations and supports a significant proportion of the scientific work carried out in the region each year. But McMurdo was built in the 1950s, and the infrastructure reflects its age. The station requires constant and expensive maintenance, and funding for upgrades has been inconsistent. Several reports produced by American scientific and governmental bodies over the past decade have flagged the deteriorating state of American Antarctic infrastructure as a strategic concern, noting that the gap between American facilities and those being built by China in particular has been growing. Sustaining scientific leadership in a place where physical presence translates into political relevance requires ongoing investment, and that investment has not always been forthcoming. The consequences of what happens in Antarctica are not confined to the continent itself. The Southern Ocean, which surrounds it, plays a critical role in regulating the global climate. The cold, dense water that sinks near Antarctica drives a system of ocean circulation that distributes heat and nutrients around the planet. Changes to the ice sheet affect sea levels that determine the sole habitability of coastal regions home to hundreds of millions of people. The subglacial ecosystems, the ice core records, the nutrient flows into the Southern Ocean, and the krill populations that feed the entire regional food web all form parts of a system that took millions of years to reach its current state and that would take far less time to disrupt significantly. The Antarctic Treaty has been held for over 60 years. That is a genuine achievement, representing a sustained commitment by a large number of nations to maintain a space that operates outside the normal framework of territorial competition and resource extraction. The scientific knowledge produced under its protection has contributed meaningfully to our understanding of climate, geology, and the possibility of life in extreme environments. That value is real, and it is ongoing. But the 2048 deadline is not distant. It is roughly 2 decades away, and the decisions being made right now about where to build stations, to conduct surveys and how much to invest in polar capability are decisions that will shape who holds influence when that review arrives. The race is not a future event. It is already underway. What Antarctica ultimately represents is a question about how the world handles something that belongs to everyone and to no one at the same time. A place whose scientific value is irreplaceable, whose ecological systems are fragile, and whose resource wealth is enormous. The nations that understand it best, that have mapped it most thoroughly, and that have built the deepest roots there will have the greatest say in what happens next. And right now, that understanding is not evenly distributed.